Practically every electrical or electronic device, no matter how small or simple it may be, has at least one of each of the following components: a resistor, an inductor, or a capacitor. A resistor has resistance measured in ohms. An inductor exhibits the property of inductance measured in henries. And a capacitor, also known as a condenser, is an electrical device that has the property of capacitance. Capacitance is the ability of a circuit or a device to oppose any change in the circuit voltage and to store electrical energy in an electric field. In general, a capacitor consists of two conducting surfaces separated by an insulating material. The conducting surfaces are called plates, and the insulating material between the plates is called the dielectric. The dielectric between the plates may be ceramic, a vacuum, glass, air, waxed paper, or any other non-conducting material. In this circuit, the blue rectangles represent a cross-sectional view of the capacitor plates. They are separated by an air dielectric. The battery supplies the electric pressure or voltage. The switch provides the control for connecting or disconnecting the battery from the circuit. When the capacitor is in a neutral state, each plate contains equal amounts of positive and negative charges. The capacitor is said to be uncharged. When the switch is closed, the battery voltage will cause an electron flow in the circuit. The positive terminal of the battery will draw electrons from one plate of the capacitor. This leaves that plate, P, with a deficiency of free electrons, which is a positive charge. At the same time, the negative terminal of the voltage source forces an equal amount of electrons onto the other plate, N. These added free electrons create a negative charge on this plate. The forced movement of electrons from one plate to another by a voltage source is known as charging, and the electron flow is referred to as a charging current. The applied voltage will continue attracting free electrons from one plate and forcing them onto the other until the voltage across the capacitor becomes equal to the maximum voltage across the source. The voltage across the capacitor has the same polarity as the charging or applied voltage. Therefore, it acts in opposition to the charging voltage. When the capacitor voltage equals the charging voltage, the two voltages offset each other, and the charging current ceases to flow. Opening the switch, the charged capacitor is disconnected from the charging voltage source. With a negative charge on one plate and a positive charge on the other, an electric field has been developed in the dielectric between the two charged plates. The voltage is present across the capacitor terminals, and the electrical energy is stored in the electric field of the dielectric. The stretched out atoms between the plates represent the electrostatic lines of force which make up the electric field, also known as the electrostatic field. Field strength is proportional to the potential difference or voltage between the plates. The action of recovering the energy stored in a charged capacitor is called discharging. In order to discharge a capacitor, there must be a complete circuit between the capacitor plates. During discharge, the surplus free electrons on the negative charged plate flow toward the positive charged plate through the discharge path. This electron flow is known as the discharge current. When all the surplus electrons have moved from the negative charged plate to the positive charged one, both plates become electrically neutral. The capacitor is fully discharged when there is no charge stored in the capacitor and the voltage across its terminals is zero. The symbol for capacitance is a capital letter C. The unit of measure for capacitance is the farad, named in honor of Michael Faraday, the scientist who advanced the concept of electromagnetic induction. The symbol for the farad is F or FD, but other symbols are sometimes used. 1 farad of capacitance is the ability of a capacitor to store 1 coulomb of charge with 1 volt of potential difference across its plates. When a capacitor is connected across a source of voltage, work is done in charging the capacitor and is stored as electrical energy. The charge of the capacitor is the measure of the energy it can store when a given amount of voltage is applied. Since a capacitance of 1 farad represents 1 coulomb per volt, the expression may be written as an equation: C equals Q over E. where C is the capacitance in farads, Q is the charge in coulombs, and E is the applied voltage in volts. Let's try an example using this formula. What is the capacitance of a capacitor that accepts a charge of 0.5 coulomb when a voltage of 100 volts is applied? Using the equation C equals Q over E and substituting the given values, C equals 0.5 over 100, the capacitance C equals 0.005 farad. The farad is much too large a unit of capacitance for practical electrical circuits. Because of this, the microfarad is used. The microfarad, abbreviated μF or MFD, is equal to 1/1,000,000th of a farad. The microfarad, abbreviated MMFD, also known as the picofarad, abbreviated PF, is equal to 1/1,000,000th of a millionth of a farad. Although the dielectric is an insulator, the voltage across the plates of a capacitor may be so great as to tear electrons through the dielectric. When this occurs, the dielectric breaks down, and arcing occurs between the plates and through the dielectric. This destroys the capacitor as it becomes short-circuited. Capacitors are therefore identified with a maximum DC voltage that can be applied across the plates. This is indicated as working volts DC, abbreviated WV or VDC, as shown on these two capacitors. These maximum voltage ratings must be observed. The simplest and most widely used form of capacitance is the paper capacitor. Paper capacitors use strips of metal foil as the plates, separated by strips of waxed or impregnated paper as the dielectric. The strips of foil and waxed paper are rolled together to form a cartridge, and the cartridge is sealed to prevent moisture leakage and corrosion of the plates. The colored ring at one end of the outside covering identifies the lead connected to the outer metal foil of the capacitor and should be connected to the low voltage side in a circuit. Paper capacitors range in value from 250 microfarads to 1 microfarad with a DC working voltage range between 100 to 1000 volts. Paper capacitors used for high voltage circuits are impregnated with oil and then sealed in oil-filled metal containers. This capacitor has threaded studs with nuts for terminals. Other types are also used. Ceramic capacitors use ceramic as the dielectric and a film of silver for the plates. They range in value from 1 picofarad to 0.01 microfarad and have a DC working voltage in excess of 2000 volts. Electrolytic capacitors are used for capacitance values from 1 to 1000 microfarads. They are polarized with the polarity of the connecting leads or terminals identified. Electrolytic capacitors must be connected with the correct polarity or they will break down and become short-circuited. This is the schematic symbol for an electrolytic capacitor. Note the polarity markings for the plate connections. The capacitance value and DC voltage rating of most capacitors is printed or stamped on the body of the capacitor. When a voltage is applied to a circuit containing a resistance and capacitance in series, the charging current is limited in value by the resistor. This limiting of the circuit current causes a time delay in charging the capacitor. The time required for the capacitor to be charged is called the time constant, abbreviated with the Greek letter tau, and is measured in seconds. The time constant is equal to the product of the circuit resistance in ohms and the capacitance in farads. It may be expressed as the equation time constant tau equals R times C. For this reason, it is often referred to as the RC time constant. The RC time constant gives the time in seconds required to charge a capacitor to 63.2% of its maximum charge. In this circuit, the resistor is 100 ohms, the capacitor is 18,000 microfarads, and the applied voltage will be 9.4 volts DC. It takes about 2 seconds for the capacitor to charge to 6 volts. That is one time constant. And it takes 5 time constants, in this example, approximately 10 seconds, for the capacitor to be fully charged to 9.4 volts. By choosing different values of R and C, the time constant T can be varied. This principle is used in many electronic circuits for timing purposes.